It's the 1 o'clock rock here on Think Tech Hawaii. We love science more than we can say. And Pete McGinnis-Mark has been a friend, a follower, a guest, a speaker on our program since 1831. Welcome to the show, Pete.
Great to be back. Nice to see you again, Jay. Happy New Year.
Happy New Year in all ways. Yeah, Shinyin Kwai La.
Yeah, indeed.
It's coming up soon. Well, I'm very excited about science, and I just came from the Pacific Telecommunications Conference down in Waikiki, and I learned again that Hawaii's great ability, its great talent in a larger sense, is to attract researchers from all over the world. And we do that. And I want to, shout it to the heavens that we do it, and we do it well. They like coming here. They like collaborating. We are very effective in collaborating with them. We are a national center of collaboration. Aloha, baby.
That's right, and indeed it's a big economic driver for the state. We bring in tens of millions of dollars to the state primarily through the attendees at various conferences and workshops, and they usually bring their families and spend some money here. So in addition to the federal research grants which we bring in, there's an added bonus that over the last couple of decades, my school's brought in perhaps $110 million in visitor fees that they pay to the hotels and rental companies and everything else.
Have you ever thought about arranging a parade in Waikiki composed only of scientists? Scientists riding
that would be
white horses down Kalakaua Avenue.
Ugly. No, definitely. Heaven forbid, no.
And whether they use a calculator or not, we give everybody a pocket protector and a small, what do you call it?
Well, a slide rule.
Slide rule, thank you.
Slide rule would be good.
I couldn't remember the name. Okay, let's talk about your research these days.
Okay.
Let's talk about space.
And we're here today primarily to make the point that Hawaii is internationally recognized as being one of the real places where researchers and engineers come primarily to try and understand the way that volcanic activity operates, because Hawaii, it's safe, it's within the United States, the access is really
And there are great hotels a few miles away.
And you have great hotels and obviously the air transportation here. So there are a variety of reasons why Hawaii has, over the last, say, 40 years, become one of the real centers where a group called planetary volcanologists, in other words,
do they have funny ears?
No, that's Mr. Spock. But planetary volcanologists will better study volcanic processes here on the Earth to understand what we see on the planet.
Yeah, you were saying before the show began, you look at a photograph of a lava flow, you can tell stuff that will be useful in space.
That's right. We'll get to that. But maybe if we'd have the first slide up, and that will actually show us. Here, for example, is an image of a volcano on planet Mars. That's in the gray tone image, and you can sort of see there's a big circular feature which surrounds the state of Hawaii. Both of the landforms, the red islands of Hawaii and the gray volcano in the background, are both volcanoes, except the volcano on Mars, which is called Olympus Mons, is about 500 kilometers across, and it's 23 kilometers in height. And indeed, the summit crater, and many of us here have heard of Kilauea volcano. Well, Kilauea has a summit crater called a caldera. The caldera on Olympus Mons is bigger than the island of Oahu. And so trying to understand how you could have created a volcano like Olympus Mons through the same types of eruption processes as has produced either Kilauea, or Mauna Loa, or Haleakala. That's why people come to Hawaii. It's the chemistry of the rocks, it's the general style of eruption and that sort of thing. So.
Can I just go back to that photograph for a minute? Now, I want to be clear here. I'm not a geologist.
Okay.
Nor am I a geophysicist or anything. But I'm looking at the shape, not of the islands in red, the shape, the texture behind them.
Right.
Which I assume is the undersea texture of
planet
Earth.
No, the texture, the gray texture, is actually a whole series of lava flows on the Martian volcano. So if you were sort of to draw a circle about 20% in from the edges of the image, you're seeing a large circle with a smaller circle, both in gray, within this image. And that is the entire volcano. All right, so you see no underwater topography here on planet Earth. All you're seeing beyond the red Hawaiian Islands is Mars.
It's a comparative thing.
It's a comparative thing.
For size.
Drawn to the same scale.
Yeah.
Drawn
But going to Mars then, for that texture in Mars, what does that suggest, that texture? It's almost the result of some viscous, phenomenon. No?
Well, over perhaps the last 3 billion years, this particular volcano on Mars has been producing lava flows that individually would look like a lava flow on Mauna Loa, for example, but in reality there are so many of them. They have produced at this level of detail, and the scale bar in the bottom right hand corner is 100 kilometers. Okay,
Yeah.
So most lava flows on Mars may only be 5 to 10 kilometers in width, but as you stand back from the planet and look at this whole volcano in one go, then you're starting to see a general texture, a filamentary texture, which is hundreds of individual lava flows.
That in itself is very, very interesting.
Right,
Yeah.
and why, just immediately looking at that particular image, the questions would be, why is the volcano so wide? Why is it so high? How long has it been erupting? Because Hawaiian volcanoes in general stay active for only like 200,000 or 300,000 years before they move away from the magma source. On Mars, to produce
The surface moves away.
the island itself, because of plate tectonics,
Okay.
drifts generally to the west.
Okay.
Well,
So if you were once right on top of the magma source, then at a later time you might be at a different place.
3.5 million years ago, Honolulu would geographically be where Kilauea is now. All right, and 1 million years ago, Haleakala would be where Kilauea is now, or 5 million years ago, Kauai would be where Kilauea is. So Hawaii is on the Pacific Ocean plate, which is generally moving sort of northwest away from the magma source. And so each of the volcanoes only has a few 100,000 to 500,000 years of activity to produce the large geologic structures which we see today. On Mars, where you've got this volcano, which is huge in comparison, you have to recognize that it's probably been active for hundreds of millions of years, and that the crust of the planet hasn't been moving around like it has done on the Earth. So that's one thing you can do. But then, as we'll see later this afternoon, there are other things where you can start playing with, say, what is the effect of the atmospheric pressure
On the movement.
on how the lava flow comes to the surface. Okay, I think probably the second image will show us. This is an image. There's no scale bar there, unfortunately, but figure that is about just the size of Oahu. So what we're seeing is an active lava lake on a moon of Jupiter called Io. And this lava lake is very similar to the lava lake which we have currently active in Halemaumau crater on Kilauea. So people who are studying spacecraft data of this moon called Io try to understand how volcanic eruptions not only create the landscape, but also we can develop instruments which measure the temperature of the lava flows. So how rapidly does it cool in the vacuum of space? And the garish colors that you see there are partly the product of the fact that there's a lot of sulfur within the surface
It's
rocks.
deposits.
The sulfur dioxide is deposited on the surface.
Yeah.
So that you're seeing the effect of sulfur on how an active lava lake might be working.
But it doesn't reflect temperature. Those
that-
colors, the garish colors, don't reflect temperature.
Correct. That particular image could not be interpreted in terms of temperatures. But there are technologies, instruments which have been first tested here in Hawaii and then flown in space in Earth orbit, where you can get very accurate temperature measurements to see how dynamic something like a lava lake, such as the one here, is shown. And I think the third image will show us somebody going out to, no, I made a mistake. But here, for example, is a different type of volcanic activity. This is an image of a moon of Saturn called Enceladus. And I brought this one along primarily because Enceladus is made out of water ice. So these bright jets, which are coming up from the limb of the moon, these are jets of probably frozen water ice. So it's water ice.
Oh, it's not heat.
Well, it's hot compared to the ambient temperature, which is about 110 Kelvin. So there is liquid water close to the surface of this moon, and it explodes into the vacuum of space. So we've already seen, all right, we've got lava flows on Mars, which are quite similar to lava flows here in Hawaii. But then on Io, we've got sulfur-driven lava lakes. And on this moon called Enceladus, we've got water geysers, which constitute the primary type of volcanic activity which we see in this particular part of the solar system. And understanding the physics of each type of eruption tells us about the interior structure of either Mars or these moons, and it enables us even to test, say, like the mathematical models that we have on how a volcano explodes. Why does it explode? It's like taking the top off of a soda bottle, for example, and the gas bubbles expand and all the magma gets thrown in the air, right? Well, if you've got the vacuum of space, or you've got a lower surface gravity like you do on the moon or you do on Mars, then you can test the numerical models to see if you've really got them right, as opposed to just making them work here on Earth, for example. And here's another example.
Where's that?
This is on our moon, all right, and the red arrow points to a squiggly line, which is actually a lava channel that was produced probably about 3.5 billion years ago. This is called Schroter's Valley, and the two circular features just above Schroter's Valley, those are meteorite craters. They are not volcanic, but each of those craters is about 40 kilometers across.
Where the arrow is, just above the arrow, it seems to be coming out of the bottom of the crater like a lava tube almost.
That's right. So this was a very energetic fire fountain. In other words, molten magma was being thrown maybe 2 or 3 kilometers up into the atmosphere. And when that molten rock lost its gas and fell back on the ground, it was so fluid that it carved the winding channel that we see in the lower part of the image.
And the winding channel, is it winding because of the terrain, the pre-existing terrain, or some other property?
In part, but also we can't see in this particular image because the detail isn't too good, but it meanders kind of like a flowing river does. So the lower reaches of the Mississippi River has these oxbow lakes where you see that same kind of feature. So we know that the slope over which this lava flow was moving was very, very shallow. We know that it stayed active for a long period of time because it actually carved some of these meandering channels. And then you can make inferences about the total volume and how long did the eruption last, and that sort of thing. And then use that information to better understand some of the ground shots. And I think the next image should show us. This is astronaut Jim Irwin for the Apollo 15 landing site. This is Hadley Rill. The black feature behind the astronaut and the rover is actually a ground view of the same kind of lava channel, but this one's about 1 kilometer in width and 300 meters deep. So, people have been to see some of these features on the moon. But here in Hawaii, they are quite often forming, and you see lava tubes as well as lava channels.
Covered with vegetation.
When they're old enough,
When they're older, down to lower elevations.
Pristine lava channels on Mauna Loa,
You can see 'em.
unvegetated, yeah, and so you can measure the width and the depth. And here, for example, we're seeing another astronaut view. This is taken from the Taurus Littrow region of the moon, which is sort of the top right as you look at the moon at night. And the orange area there, that is volcanic ash, which was produced by one of these fire fountain events. So what we need to understand on the moon is how explosive does the eruption have to be to disperse this kind of ash all over the lunar surface? What volatiles will actually drive an explosion? There's very little water on the moon, so it's probably carbon monoxide or other kinds of gases. So here, I think in the final slide of this set, this is another explosive eruption. This one is on, again, the moon Io on Jupiter. And here we're seeing sulfur dioxide producing a giant umbrella cloud, which is about, say, over 1,000 kilometers across. So all of these...
And you can tell that from with the spectrum of color.
You can infer a lot about the particle size and the composition from a variety of images, not just from this one photograph, but we know because we've got additional data for this particular eruption. It's been active since at least 1979, still ongoing. We know how high the eruption counts go, so how much energy do you need to put into the magma in order to throw it this height above the surface?
Peter McGinnis-Mark, researcher at SOWEST and HIGP, makes you want to know more about geophysics, and it makes you want to erupt into a break. We're going to take a break.
Okay, sounds good.
Aloha, my name is Justina Spiritu, and I'm the co-host of Hawaii Farmers Series. This is my co-host, Matthew Johnson, and you can catch us every Thursday at 4 p.m. at thinktechhawaii.com. What do we talk about, Matt?
So on Hawaii Farmers Series, we're going to be bringing on the farmers and also supporter of farmers, including restaurants, caterers, as well as government supporters and nonprofits to hear their background stories and understanding our local ag community just a little bit better.
Yeah, essentially, there's a lot more that goes into farming and the local food community beyond just producing the food. And we want to feature and get the background story on all these folks and see how we all work together as a community. So join us every Thursday. Aloha.
Bingo, 1 o'clock rock. Peter McGinnis-Mark, research in Manoa from SOWEST and HIGP. And if you didn't know this, before, write it down. Hawaii Institute of Geophysics and Planetology. It is a very important name. It's an important part of Hawaii's intellectual property, as far as I'm concerned. So, what's interesting is that the rules of physics are universal in the world. I mean, you'd have to go pretty far out there.
In the galaxy, not just the world, yes.
Okay, the galaxy.
Right.
Okay, beyond the galaxy, we don't know.
Well,
Right?
it would work in other galaxies as well.
How do you know that?
Because there's no reason to suppose it doesn't work that way.
Someday,
But
we're
you
going to
can,
go there and
you
find
can
out
look
for
at other
sure.
galaxies and they perform in the same way that our one does.
And you can tell by light
You
and
can
all
t-
this.
Yeah.
Yeah. Okay, so the rules of physics are really important. But the other thing that I get out of this is that we don't know all the rules yet. We don't know all the rules that pertain to volcanic development, eruptions, what have you. And we need to find out exactly how it works. And we look here, under our feet to find out how it works there, millions of years away.
Yes, and you could also invert that to say we look elsewhere to understand what it was like here at an earlier time in Earth's history, which has subsequently been destroyed.
Yeah.
So it works both ways. It works both ways.
So, a question I put to you, though, is this is pretty far removed from daily life.
Unless you lived in Pahoa, and you had a lava flow coming in towards the subdivision, yeah, it's far
Or
removed.
Krakatoa, maybe.
Or you lived in Honolulu 8,000 years ago, and there
Yeah.
was 6 meters of ash deposited from the mountaintop. Yeah,
bad day.
Bad day in Honolulu. So, or when Diamond Head went off. Yeah.
So I guess what you're saying is this whole inquiry becomes interesting because while we here in 2016, have a relatively, sedate Earth, relatively speaking, it's not always going to be that way, and we have to understand how it's going to change.
Right, and in Hawaii, it's particularly relevant, say on the Big Island, there's a guy who used to be chief scientist, Don Swanson, who still works at the Hawaiian Volcano Observatory, has recognized, for example, the Kilauea volcano only about 400 years ago was in a highly explosive phase. And we automatically assume, because we just have nice quiet lava flows right now on Kilauea, that it's always been a mild type of volcano. Not true. It had some huge explosive eruptions. So
You're going to tell us, press release, come on the show, something. You're going to say when this is going to happen again with the 400-year
no, it's just,
cycle.
the Hawaiian Volcano Observatory does a really good job in that.
Okay.
That's-
But you are here to tell us that it can and will happen again.
It's common knowledge within the scientific community, particularly HVO scientists do a really good job. Tina Neal is chief scientist there. They inform the public. They are well aware of some of the risks of the volcanic eruptions. And I mentioned, lava flows going into Pahoa, or the fog which goes down towards Pahala, for example. This is a whole series of issues related to the current volcanic activity, but HVO staff do a superb job in informing the national park and the local community. So my group at Manoa doesn't really take that responsibility on. We just leave it to the
So
experts.
I wouldn't assign it to you, except, I like to read your stuff and maybe know about it. So question is, this leads to, pretty basic geological questions too. If you tell me that there are large, if not, plenary tracts in the state of Hawaii that were created by volcanic activity at one time or another, by geological seismic activity, one kind or another, then that helps me understand what's under my feet and what I'm building on and what I'm digging into.
Hawaii is 100% volcanic.
Thank you.
All right, so anywhere we live in the islands, you will see volcanic landforms, and we'll get into this in the third segment, where you can go on Oahu or on the Big Island to see these sort of volcanic features. But yes, you're correct in saying that although studying volcanism on the planets is exotic and may not have direct relevance to our everyday lives, we then have the ability to test these numerical models or see the diversity of volcanic eruptions elsewhere in the solar system, because we haven't been making scientific measurements on Earth long enough to see the full spectrum of volcanic activity.
So at the very least, it's validation.
At the very least, it's validation, but more importantly, it gives us a better understanding on how to interpret volcanic features and the range of explosive or highly effusive activity. So it really does help us. What's the role of water in producing giant ash explosions that, say, produced Diamond Head or Cocoa Head and Cocoa Crater and that sort of thing? How often do they occur? How close would you be and be injured by such an eruption? So there's a lot of practical things to worry about as well. And we also try to understand the internal structure of a volcano, so that it's not just the surface layers that we're interested in. Obviously, a volcano is three-dimensional. So what's going on inside the volcano? How does it grow inside? That impacts a whole variety of things, not only the volcano itself, but groundwater resources. Where does fresh water collect?
Interaction with other elements of the environment.
How does rainfall actually percolate through the interior of the volcano towards the ocean? Because all of our drinking water here in Hawaii relies on rainfall that has been trapped underground. Well, parts of the volcano pass water really easily, ash layers, for example. Other parts of the volcano, that part of the plumbing system that feeds the magma at the surface, is almost, it's a barrier, it's impermeable to water. So not only do we want to know what the risks are of a volcanic eruption, but we also want to know the inside of the volcano, because that is where we get our drinking water from. That is a whole series of other geologic hazards, like the occurrence of earthquakes, as well as, say, if you get landslides around the island. So many of the valleys here on southern Oahu, the volcanic rock weathers into a clay which swells when it gets wet and contracts when it's dry. And so if you're building your house in an area where there's clay, then you're going to get ground cracks. So here we've got a photograph. This is just to give you some idea of how a planetary volcanologist would come and study Hawaii. This is from a satellite. We are looking at the southern flank of Kilauea volcano. The white dot just in the sort of above center, that is Halemaumau crater. So we're looking at the southwestern rift zone of Kilauea, and there hasn't really been any volcanic activity there since December of 1974. If we go to the next slide, this is exactly the same area, except instead of using optical wavelengths of light to produce the colors, here we're using radar, or we're bouncing microwave energy from the space shuttle to look at the same features. Why do we want to do this, you ask, Jay? Well, if we go to the next slide, what we'll see is this is another volcano elsewhere in the solar system. This is Sapus Mons on the planet Venus. And Venus has an atmosphere that's 100 times as thick as the Earth's. And you can't take regular photographs through that thick atmosphere.
The light doesn't travel the same way.
The light doesn't travel, so you have to use radar to actually make the measurements. And in the next slide, we'll see this is what the radar system looks like. I was part of a team that flew 3 radars on the space shuttle between '94 and 2001. The Jet Propulsion Lab, JPL, and Langley Research Center in Canada are all represented there. But basically, learning how to use different types of instruments to study the planets also helps us understand the Earth. The next slide would show this is a series of lava flows on Mauna Loa. The part of the image at top left is a color photograph taken from an airplane, but the rest of the image is a thermal infrared image, which tells us a lot more about how the chemistry of Mauna Loa has been developed.
What's hot, what's not?
Yeah, basically.
No, but what color is hot?
Oh, these are random. This is a technique which just enhances the color differences. None of the data there lets you determine how hot the lava flows are. And we're looking at prehistoric lava flows up to about the 1942 lava flows. So these are all cold to the human touch,
yes.
Right? But if you go to Mars, this is the same instrument that took the previous type of image, except we're looking at volcanic channels on the surface of Mars. So again, using Hawaii as a planetary analog to better understand how to build and test and interpret instruments that inform us about what the volcanic structure is like, what the lava chemistry is like. Hawaii has been at the forefront worldwide of this particular technique. We first flew a shuttle experiment in 1984 over Hawaii, and since that time we've always been using Hawaii, primarily Kilauea, but sometimes Mauna Loa, as this geological test site to better understand how to measure volcanoes and volcanic landforms on other planets.
And that is likely to continue for the next 40 seconds or a minute or so.
Oh, at least, yes.
Okay,
Perhaps
then we can
even
take a
longer.
break.
Yeah.
That's why we will take a break.
Okay.
Aloha, this is Keli'i Akina, president of the Grassroot Institute, and I want to thank you for watching ThinkTech Hawaii. We are delighted to be partners with ThinkTech because it gives us the opportunity to bring to you a show every week on Monday at 2:00 p.m. called Ehana Kako. Ehana Kako means let's work together, because we believe that Hawaii will be a better place when everybody works together. And in what way? Well, at the Grassroots Institute, we research 3 basic areas, and we invite guests to come on board from across the country, the state, and the nation to talk about a better economy, a better government, a better society. Now, aren't those things we all want? Indeed. If you'd like to have the latest research in terms of public policy, as well as ways in which we can build a better government, economy, and society, then tune in every Monday on Think Tech Hawaii at 2:00 p.m. for our fascinating guests on Ehana Kako. Let's work together. I'm Keli'i Akina with the Grassroots Institute, and I'll see you then. Aloha.
Bingo, we're back with Pete McGinnis-Mark, researcher of Hawaii Institute of Geophysics and Planetology in the School of Ocean, Earth Science and Technology at UH Manoa, as part of our Research in Manoa program every Monday at 1 o'clock. And we have some more slides. We have some more slides, right, Pete? Let's
We
go
have
to-
some more slides. And so in this final segment, I wanted to make it clear that this isn't something which only scientists can do. For example, anybody who's living here on Oahu can go to world-class places where you can better understand how a planetary volcano has operated. Some of you might remember or recognize Koko Crater here in green on New Year's Day only a couple of weeks ago. But at the foot of Koko Crater and at Lanai Lookout, there are these layers of ash which were produced when you had an eruption on Oahu that took place just offshore. And so you had explosive eruptions that each eruption produced one of these ash layers. This is almost certainly very similar to the styles of volcanism which were associated with the early periods of volcanism on Mars.
So that picture in the lower left inset, that's like a previous version of, what is this, Cocoa Head?
Well, it's just an exposed part of the same crater, all right? So you can sort of see that the road which goes around Hanauma Bay to Lanai Lookout to Sandy Beach, right at the Lanai Lookout, instead of looking out to the ocean, if you just turn around, there is the exposure.
It's a today picture.
Today picture, yeah. And that set of ash deposits is used by people from all over the country to better understand how the interaction of hot rock and abundant water, the ocean, can produce explosive eruptions in the same way that abundant water early in Martian history would have interacted with lava flows. I think the next slide will show us. Next. Here's another goodie. You would have to get permission to go to this venue, because this is the rock quarry going over to Kaneohe, and the giant dumpster truck is there for scale. But if you were to look at, say, from the Pali Lookout going out towards Kaneohe Bay, that is the central portion of the old Koolau volcano. And you might just be able to see there are a whole number of vertical lines in this particular image. Those lines are dense volcanic rock which was squeezed into the pre-existing country rock as new eruptions forced their way up to the surface. And in some places, as in this rock quarry, these blades of volcanic rock, and the blades are called dikes, constitute about 60% of the volume. And all Hawaiian Islands are surrounded by giant landslides. Like East Oahu fell into the ocean probably about 1.5 million, 2 million years ago. As a
Kailua also fell into the ocean.
Yeah, as a consequence of these dikes being intruded. So as we study the spatial distribution of where lava flows are erupted on the surface, each one of those lava flows below the surface have to have one of these dikes beneath them. And so for Oahu, trying to understand where these dikes were forming and what their orientation was with respect to the island helps explain the occurrence of these giant landslides. And in particular on the Big Island, that's important because as Mauna Loa and Kilauea continue to grow, there are more dikes being intruded, so you're getting this oversteeping. Here we see one of the examples of what we do with our graduate students or some of the workshops which we lead. So we go out into the field and we make measurements on the thickness of layers, and we've got various instruments which measure the temperature or the chemistry and that sort of thing. I think we'll see another example in the next slide, where we're looking at what is called a tumulus, which is basically a lava blister. This is out on Kilauea volcano. And so this is a very common feature on Venus and on Mars, and it's formed where the surface topography is a very shallow gradient. So we get people climbing all over them, and we look at the internal structure because these cracks,
You can see down into
you
them.
can see inside the cracks. Next slide should give us. This is another example. Really exciting stuff here. This is an active lava tube. We're seeing it through a skylight. And this is a subsurface pathway. Recall at the beginning of the show, we saw that sinuous lunar channel. We saw the astronauts standing by the side of one of these channels. Understanding how they form here on Kilauea is really important, and here we're just about to make temperature measurements, not only looking into the skylight, and it's about 1150 centigrade, so it's quite hot, but also you can map out the temperature distribution going away from the central lava channel.
This is near Kilauea, the Big Island.
This is on Kilauea. This is on the southern flank of
Now, what's
Kilauea.
remarkable to me is that hot area to the left at the bottom. That's
That's pretty hot.
That's molten lava down there.
Yes,
huh?
yeah.
You wouldn't want to take a walk down there.
No, you couldn't.
Yeah, you couldn't.
Yeah.
Now he's safe though. There's somebody on top of it.
Absolutely, absolutely.
Because
yes.
it looks like it's gee whiz, at
There's
least
a-
6 feet deep, tall.
Yeah, but
thick.
but there's at least 2 meters of solid rock between the people and the underlying lava tube. Yeah. Let's take a look at the next slide. And you can get a lot closer, but here one of my colleagues, Scott Rowland, needs to have an asbestos helmet and gloves. Scott is actually sticking a thermometer into a still moving lava flow. So even though we can build all these fancy gizmos which measure the temperature remotely, because
Yeah.
that's what you do on the planets,
Yeah.
it still helps to have real in situ measurements. And in this particular case, Scott is making the temperature measurement of a cooling lava flow.
Let me just digress for a moment about it. That's a special thermometer. That's not, you can't buy that at Long's drugstore, for example.
No, but you can buy it at Radio Shack.
Is that right?
Yeah, Long's doesn't sell them. We've already
But
discovered
late
that.
Radio Shack,
But yeah, just
thermometer.
well,
Isn't it going to melt?
it's not an ordinary thermometer. I mean, it's not one of these glass.
It's like a
things
meat
with-
thermometer you put in the oven?
It's very similar to a meat thermometer, and you just have to calibrate it. Instead of having your lamb roast, which might be like 475 on the grill, you need to have the thermometer calibrated so that at least you can get temperatures up to about 1200 centigrade. But it's the same principle as a thermometer for your
So this goes to, we know we want to measure a ton of stuff. We want to take
Everything.
everything we can possibly think
Anything
of.
and
you know.
everything.
That's
Why
the
not?
joy of being a scientist.
It's
You
science.
always want more data. Yeah.
Yeah.
and in order to get the data, you've got to have methodologies and instruments
Yep.
to go out and do it. So
Right.
sometimes it's a Safeway, sometimes it's not.
Sometimes it's a Radio Shack. That's right. But
And so you keep on trying to find sensors.
Or
if
you
will.
build them. Or you build them
You
yourself.
build them
Or you
yourself.
build them yourself. There's some of the more complicated ones, which would be like these thermal cameras, which let you not only measure temperatures remotely, but also the chemistry or the imaging radar systems. They are custom made. You cannot buy them even at Sears or anything like that. But horses for courses. As you start to understand the way the volcano is working and what measurements or what data you're lacking, then you can start designing which instruments you need to either fly or take into the field or put in orbit. So you look at the geographic area of coverage, the spatial resolution you need, the temporal coverage you need, and how precise do you need to make a particular. I mean, it's all basic. It's
basic.
straightforward.
It's your basic innovation
Yeah,
experience.
it's a high-tech innovation, yes, and pushing the envelope in terms of, always wanting to make better quality measurements, always wanting to have supplemental data sets. How do you measure topography over which the lava flow is moving? Either you use drones or you use a laser altimeter, or there are other stereo techniques. So in the past, we were happy to just look at a contour map from the US Geological Service. Now we need, say, topography with a 5 centimeter spatial resolution and 2 centimeter vertical accuracy in order to predict where the lava flows. And I think if we go on to
have a
the
movie
video,
clip now. You
we've
wanna
got a
see that?
movie clip.
Let's
I
see
think
the
we may
movie
have
clip.
to go one forward, but we should. Okay, so what we've just seen is basically a short video clip of active lava flow on Kilauea. And the type of measurements which we would need not only will be, of course, want to know the temperature distribution across the whole lava flow at a high spatial resolution, but we also need to know what is the topography of the ground before the lava flow is moving. And that's really an important attribute, because if we were to help the USGS and the people at Pahoa, for example, and telling them where is the lava flow likely to go, the lava flow isn't water, but it does flow downhill. And so understanding the pre-existing topography, understanding how the topography influences the flow and where the lava flow stalls and maybe inflates a bit, those are the sorts of things. We need better measurements of that kind of phenomenon, not only to better understand the physics of how lava flows erupt and move, but also practicalities, disaster management, civil defense.
So if I'm a researcher or, say, a graduate student working on something like that,
You'll have a lot of fun.
I know I would.
Guaranteed. Yeah, big fun.
I would design a spreadsheet with all these fields, right? Because each field represents a different kind of measurement. And then I'd have a time factor on it, and then I'd be writing all this data into each field.
And the real challenge for a graduate student, for example, is actually to identify a specific subset of all of these fields in your spreadsheet, because it's now got so complicated. You can't build or design, say, an imaging spectrometer as well as a thermal camera, as well as a topographic mapper from day one. So a student really has to find out where is her passion for this type of work, what aspects of the background research haven't been covered yet, and what the contribution will be. And this is a final slide where you can go out into the Ka'u Desert of the big southwest rift zone of Kilauea. These black circles are actually big pit craters, which the student in the bottom there, now covered up by the logo at the bottom, is actually standing in. But trying to find an aspect of volcanism on the planets, or even understanding volcanoes and how they work here on the Earth. Coming to Hawaii and sort of being able to go into the field, having the planetary context, as well as the instrument development, the high-tech aspect of doing volcanology. That's where Hawaii really is one of the world leaders. We've got all of the attributes here. It's easy to get to, it's relatively safe. We're also a world leader in terms of understanding the way Hawaiian type of volcanoes work. And we don't understand all of the volcanoes of the world, but the type we have here in Hawaii also occur in the Galapagos Islands, in Iceland, Reunion Island in the Indian Ocean, for example. And we have great volcanologists. We have Bruce Houghton, who's the state volcanologist, for example, at Manoa.
Where can I find out more?
Well, we have websites. The School of Ocean, Earth Science and Technology has its own website, soest.hawaii.edu.
Okay.
Will give you the links to the individual departments. So my institute, Hawaii Institute of Geophysics of Planetology, would be higp.hawaii.edu, and then you can just sort of troll through various websites. We have, as part of the Pacific Regional Planetary Data Center, a special segment of that website which focuses on Hawaii as a planetary volcano analog, for example.
And of course, you can come back and discuss this further.
Delighted.
That is another
It's
logical
always a
possibility.
pleasure. It's
Thank
always-
you, Peter McGinnis.
Jay, thanks so much for having me back again.
HIGP,
Till next time.
Research and Manoa. Till next time.